In this video, I'm going to finish a project that has sat in my office unfinished since 2011, my desktop CNC machine. A CNC machine is a tool that can automatically cut a design out of a material like wood or metal. The design starts out on a computer and is converted into machine instructions called G-code. The CNC machine will read the G-code one line at a time and remove material until the entire design is cut out of the material. A CNC machine is made up of several parts. The part that actually does the cutting is called an end mill. An end mill is similar to a drill bit. The difference is that after an end mill has been plunged into the stock material, it can be moved around side to side and it will still cut material away. The end mill is inserted into the spindle motor, which rotates it at a controlled speed. This subassembly, which I'll refer to as the cutting tool, is attached to a mechanical frame. The frame is built with gantries that allow the cutting tool to move in the X, Y, and Z axes. That movement is achieved by attaching stepper motors to belts, pulleys, and lead screws. Stepper motors are ideal for this application because of their precision, but they require special electronic drivers that energize their coils in a specific sequence. In the past, it was common to use a computer with a parallel port to talk to the stepper motor drivers, but nowadays, microcontrollers with a UART connection are becoming more popular. For my CNC machine, I'm using an Arduino-compatible board running a special firmware called Gerbil. The G-code instructions are sent to the Arduino by a computer, and the Gerbil firmware interprets that G-code and sends the step pulses and direction signals to the stepper motor drivers. Lastly, most CNC machines have input switches that send feedback from the machine. For example, my machine has limit switches that close when the machine reaches the end of its range. This prevents the machine from moving beyond its physical limits and causing damage. If you want to know more about my CNC machine, I've written a detailed project post on my website, and I'll leave a link in the description. This project has been on my to-do list far too long. Before I can check off the box next to this project, I want to complete 4 specific things. First, I want to put in a proper power supply. Right now I'm using the power supply from a desktop computer, and I want to use one that's specially made for this application. Second, I want to wire up the start, stop, and pause buttons. Right now these buttons are installed, but they're not wired up to anything. These buttons make it easier to interact with the CNC machine instead of using the software. Third, I want to work on cable management so that there aren't wires going all over the place. Finally, I want to swap out the Dremel rotary tool that I've been using for a 400-watt brushless DC spindle. Banggood.com was kind enough to send me one to use in this project. Once I get these things done, I want to fire it up and demonstrate what this kind of machine can do. Before I get started on my list, I want to modify the base of the CNC machine. As you can see here, I've built a plywood enclosure that has a hinge on one side. The idea was to be able to lift up the machine to access the storage area underneath and put electronics in there. I've decided I don't like this design, so I removed the hinge and cut the box in half on my table saw. I think this shorter box enclosure will fit my needs better. Now I'm ready to upgrade the power supply. First, I removed the old computer supply and put in 2 new supplies. The one on the left is a 24-volt, 360-watt supply for the stepper motors. The one on the right is a 48-volt, 480-watt supply for the brushless DC spindle. I installed an IEC connector that is equipped with a switch and a fuse. This makes it easy to turn on and off everything with one switch. The fuse adds an extra layer of safety should anything go wrong. Once I got the AC side wired up, I plugged everything in and powered it up. I adjusted the knob on the spindle supply until I measured 48 volts on the output. Next, it was time to wire the 24-volt terminals to the stepper motor drivers. I used spade terminals on all wires to ensure reliability. You can insert stranded wire directly into these screw terminals, but I wouldn't recommend it. Here's how things looked after getting these wired up. I had these 3 arcade-style buttons lying around, so I used them for the start, stop, and pause buttons. I need to wire them up to the Arduino board using some shielded cable with twisted pairs. In a minute, I'll talk about why I chose shielded wire for these switches. I stripped the ends of the wire, tinned them, and soldered them to the switches. I covered the joints with heat shrink tubing and aimed my heat gun at them. The next step was to wire them to the Arduino. Up until this point, I had been using an Arduino Nano breakout board with screw terminals to make all the connections. The screw terminals were oversized for the gauge of wire I was using, and they kept coming out, so I ended up ditching the breakout board and just soldering the wires directly to the Arduino. This is the permanent home for this Arduino board, so I'm not worried about soldering everything permanently. This left me with no way to mount the Arduino board to the plywood box, so I jumped into Fusion 360, designed a mount, and printed it out on my 3D printer. Did I mention I love having a 3D printer for things like this? The most time-consuming part of this whole project was cable management. Up until this point, I had stepper motor and limit switch wires going all over the place. The motors and power supplies in this machine can cause quite a bit of electromagnetic noise that can interfere with other parts of the system. The first thing I wanted to do was remove the old wiring and replace it with new shielded wiring. The reason I went with shielded wiring this time was to reduce the effect of the electromagnetic noise created by the power supply and the motors. The problem was so bad before that I was actually getting noise on the limit switch wires that were causing false positive readings on the limit switches, even though they weren't even being closed. Using shielded wire and connecting that shielding to ground significantly reduces the electromagnetic noise seen on that wire and pretty much eliminated all of the false positive triggers I was getting. Now that the wiring is complete, it's time to get them under control. I ordered some drag chain that solves this problem beautifully. I needed a way to mount the drag chain to the frame, so I modeled some parts in Fusion 360 and printed them out. I routed all of the wires through the drag chain. The last step was to put connectors on everything. I chose 6-pin DIN connectors for all the motor wiring and limit switches. The last step for completing my CNC machine was to upgrade the spindle. I was using a Dremel rotary tool before, which works, but it's not the ideal tool for this job. I also think that the Dremel was contributing to the EMI issue I was having. I asked my friend Dan, who is an expert on CNC machines, what I could do about this problem, and he recommended that I get a brushless DC spindle. A couple of months ago, Banggood.com reached out to me and asked how they could support this channel. I asked them to send me a 400-watt brushless DC spindle like Dan had recommended. They were incredibly supportive and sent this one to me. I told them that I would test it and give an honest review of the product. I will leave a link in the description where you can buy one of these. I asked Dan to help me make a mounting adapter for this spindle. He was extremely helpful and generous with his time, so thank you very much, Dan. This mount fits the slots in the Z-axis aluminum extrusion. When I went to bolt the spindle to the mount, I noticed that the pre-drilled holes on the Banggood spindle mount weren't aligned very well. I think that I may have just been unlucky with the one I was sent. We were able to make the holes a little larger with the file and get things to fit just right. Other than that, I'm very happy with this spindle. It takes an input voltage between 20 and 50 volts DC. It has one switch to turn the spindle on and off, one switch to change between clockwise and counterclockwise rotation, and a potentiometer to control the speed. I had no trouble connecting this up to the power supply I bought and getting it up and running. One other complaint I have about the spindle driver is that it has a 10-volt analog input pin to control the speed. On the other hand, the Arduino I'm using for my controller will only output a 5-volt digital PWM signal. I'm not able to connect the Arduino output directly to the spindle driver. I will have to convert the 5-volt PWM signal into a 10-volt analog voltage. This isn't a huge deal, but it would have been nice to have the option to connect it directly. Even though I had a problem with the crooked holes and the spindle control signal, I would still recommend buying this spindle if you're going to build a CNC machine. A huge thanks goes to Banggood.com for supporting this video. I think that's everything on my list. This machine is far from being complete, but it's at the point where I can start using it. I wanted to run a test cut, so I loaded my bite-sized logo into the controller software. The blue toolpath is where the end mill will cut the logo into the wood. I put a scrap piece of pine 1x6 and secured it with tape. I lowered the end mill down to the corner of the wood and started the job on the computer. I was super excited to watch this thing spring to life. I have been working on this project for many years to get to this point, and it was very rewarding to see it come to fruition. I sanded the finished logo and applied some walnut-colored stain. This should give you an idea of what a small CNC machine could be used for. I didn't build this machine so I could cut out simple logos in wood. With the right end mills, you can cut out complex shapes out of wood, metal, foam, or even plastic. There are so many projects that all of a sudden become possible when you have a machine like this. I originally wanted to build this machine so I could mill my own circuit boards. I pulled up a design I've been working on and used some software to create the toolpath for milling out the copper traces on the circuit board. I loaded the copper clad into the work area and secured it down with some double-sided tape. I drilled the through holes with a 1.2mm drill bit. Then I swapped that out for a 30-degree engraving V-bit. This was my first time going through this process, so I didn't have high expectations. This first attempt didn't turn out very good, but you get the idea. I know it will take some trial and error to get the right cutting depth for the V-bit. I also need to make sure that I have a flat work surface so that the V-bit is evenly cutting across the surface of the copper clad. I am so happy to have finally finished this project. Like I said, I've been working on this since 2011. I think this was a great machine to start out with because of its size. However, I know that I will soon grow beyond its limited work area, which is about 6 inches by 6 inches. I already have plans for a larger machine with a work area of 1 meter by 1 meter, which will allow me to build much bigger projects. That's it for this video. I've posted a couple other videos right here that I think you might like. I make a lot of other project videos like this on my channel. If that's something you're into, subscribing to Bite Size will help YouTube's algorithm find and recommend more videos like this for you to watch. Thanks for watching, and I'll see you next time.